gravity, the most familiar of nature's forces, offers us simultaneously the best and the least understood phenomena in nature. It took the mind of the millennium's most brilliant and influential person, Isaac Newton, to realize that gravity's mysterious action at a distance arises from the natural effects of every bit of matter, and that the attractive force between any two objects can be described by a simple algebraic equation. It took the mind of the last century's most brilliant and influential person, Albert Einstein, to show that we can more accurately describe gravity's action at a distance as a warp in the fabric of space-time, produced by any combination of matter and energy. Einstein demonstrated that Newton's theory requires some modification to describe gravity accurately to predict, for example, how much light rays will bend when they pass by a massive object. Although Einstein's equations are fancier than Newton's, they nicely accommodate the matter that we have come to know and love. Matter that we can see, touch, feel, smell, and occasionally taste. We don't know who's next in the genius sequence, but we've now been waiting nearly a century for somebody to tell us why the bulk of all the gravitational force that we've measured in the universe, about 85% of it, arises from substances that do not otherwise interact with our matter or energy. Or maybe the excess gravity doesn't come from matter and energy at all, but emanates from some other conceptual thing. In any case, we are essentially clueless. We find ourselves no closer to an answer today than we were when this missing mass problem was first fully analyzed in 1937 by the Swiss-American astrophysicist Fritz Zwicky. He taught at the California Institute of Technology for more than 40 years, combining his far-ranging insights into the cosmos with a colorful means of expression and an impressive ability to antagonize his colleagues. Zwicky studied the movement of individual galaxies within a titanic cluster of them, located far beyond the local stars of the Milky Way that trace out the constellation Coma Berenices, the hair of Berenice, an Egyptian queen in antiquity. The Coma cluster, as we call it, is an isolated and richly populated ensemble of galaxies about 300 million light-years from Earth. Its 1,000 galaxies orbit the cluster's center, moving in all directions like bees swarming a beehive. Using the motions of a few dozen galaxies as tracers of the gravity field that binds the entire cluster, Zwicky discovered that their average velocity had a shockingly high value. Since larger gravitational forces induce higher velocities in the objects they attract, Zwicky inferred an enormous mass for the Coma cluster. As a reality check on that estimate, you can sum up the masses of each member galaxy that you see. And even though Coma ranks among the largest and most massive clusters in the universe, it does not contain enough visible galaxies to account for the observed speeds Zwicky measured. How bad is the situation? Have our known laws of gravity failed us? They certainly work within the solar system. Newton showed that you can derive the unique speed that a planet must have to maintain a stable orbit at any distance from the Sun, lest it descend back toward the Sun or ascend to a farther orbit. Turns out, if we could boost Earth's orbital speed to more than the square root of 1.4142, times its current value, our planet would achieve escape velocity, and leave the solar system entirely. We can apply the same reasoning to much larger systems, such as our own Milky Way galaxy, in which stars move in orbits that respond to the gravity from all the other stars, or in clusters of galaxies, where each galaxy likewise feels the gravity from all the other galaxies. In this spirit, amid a page of formulas in his notebook, Einstein wrote a rhyme, more ringingly in German than in this English translation, in honor of Isaac Newton: look unto the stars to teach us how the master's thoughts can reach us. Each one follows Newton's math silently along its path. When we examine the Coma cluster, as Zwicky did during the 1930s, we find that its member galaxies are all moving more rapidly than the escape velocity for the cluster. The cluster should swiftly fly apart, leaving barely a trace of its beehive existence after just a few 100 million years had passed. But the cluster is more than 10 billion years old, which is nearly as old as the universe itself. And so was born what remains the longest-standing unsolved mystery in astrophysics. Across the decades that followed Zwicky's work, other galaxy clusters revealed the same problem, so Coma could not be blamed for being peculiar. Then what or who should we blame? Newton? I wouldn't. Not just yet. His theories had been examined for 250 years and passed all tests. Einstein? No. The formidable gravity of galaxy clusters is still not high enough to require the full hammer of Einstein's general theory of relativity, just 2 decades old when Zwicky did his research. Perhaps the missing mass needed to bind the coma cluster's galaxies does exist, but in some unknown, invisible form. Today, we've settled on the moniker dark matter, which makes no assertion that anything is missing, yet nonetheless implies that some new kind of matter must exist, waiting to be discovered. Just as astrophysicists had come to accept dark matter in galaxy clusters as a mysterious thing, the problem reared its invisible head once again. In 1976, the late Vera Rubin, an astrophysicist at the Carnegie Institution of Washington, discovered a similar mass anomaly within spiral galaxies themselves. Studying the speeds at which stars orbit their galaxy centers, Rubin first found what she expected: within the visible disk of each galaxy, the stars farther from the center move at greater speeds than stars close in. The farther stars have more matter, stars and gas, between themselves and the galaxy center, enabling their higher orbital speeds. Beyond the galaxy's luminous disk, however, one can still find some isolated gas clouds and a few bright stars. Using these objects as tracers of the gravity field exterior to the most luminous parts of the galaxy, where no more visible matter adds to the total, Rubin discovered that their orbital speeds, which should now be falling with increasing distance out there in Nowheresville, in fact remained high. These largely empty volumes of space, the far rural regions of each galaxy, contain too little visible matter to explain the anomalously high orbital speeds of the tracers. Rubin correctly reasoned that some form of dark matter must lie in these far-out regions, well beyond the visible edge of each spiral galaxy. Thanks to Rubin's work, we now call these mysterious zones dark matter halos. This halo problem exists under our noses, right in the Milky Way. From galaxy to galaxy and from cluster to cluster, the discrepancy between the mass tallied from visible objects and the object's mass estimated from total gravity ranges from a factor of a few up to, in some cases, a factor of many hundreds. Across the universe, the discrepancy averages to a factor of 6. Cosmic dark matter has about 6 times the total gravity of all the visible matter. Further research has revealed that the dark matter cannot consist of ordinary matter that happens to be underluminous, or non-luminous. This conclusion rests on 2 lines of reasoning. First, we can eliminate with near certainty all plausible familiar candidates, like the suspects in a police lineup. Could the dark matter reside in black holes? No, we think that we would have detected this many black holes from their gravitational effects on nearby stars. Could it be dark clouds? No, they would absorb or otherwise interact with light from stars behind them, which bona fide dark matter doesn't do. Could it be interstellar, or intergalactic, rogue planets, asteroids, and comets, all of which produce no light of their own? It's hard to believe that the universe would manufacture 6 times as much mass in planets as in stars. That would mean 6,000 Jupiters for every star in the galaxy, or worse yet, 2 million Earths. In our own solar system, for example, everything that is not the Sun adds up to less than 1/5 of 1% of the Sun's mass. More direct evidence for the strange nature of dark matter comes from the relative amount of hydrogen and helium in the universe. Together, these numbers provide a cosmic fingerprint left behind by the early universe. To a close approximation, nuclear fusion during the first few minutes after the Big Bang left behind 1 helium nucleus for every 10 hydrogen nuclei, which are, themselves, simply protons. Calculations show that if most of the dark matter had involved itself in nuclear fusion, there would be much more helium relative to hydrogen in the universe. From this we conclude that most of the dark matter, hence, most of the mass in the universe, does not participate in nuclear fusion, which disqualifies it as ordinary matter, whose essence lies in a willingness to participate in the atomic and nuclear forces that shape matter as we know it. Detailed observations of the cosmic microwave background, which allow a separate test of this conclusion, verify the result: dark matter and nuclear fusion don't mix. Thus, as best we can figure, the dark matter doesn't simply consist of matter that happens to be dark. Instead, it's something else altogether. Dark matter exerts gravity according to the same rules that ordinary matter follows, but it does little else that might allow us to detect it. Of course, we are hamstrung in this analysis by not knowing what the dark matter is in the first place. If all mass has gravity, does all gravity have mass? We don't know. Maybe there's nothing wrong with the matter, and it's the gravity we don't understand. The discrepancy between dark and ordinary matter varies significantly from one astrophysical environment to another, but it becomes most pronounced for large entities such as galaxies and galaxy clusters. For the smallest objects, such as moons and planets, no discrepancy exists. Earth's surface gravity, for example, can be explained entirely by the stuff that's under our feet. If you are overweight on Earth, don't blame dark matter. Dark matter also has no bearing on the moon's orbit around Earth, nor on the movements of the planets around the sun, but as we've already seen, we do need it to explain the motions of stars around the center of the galaxy. Does a different kind of gravitational physics operate on the galactic scale? Probably not. More likely, dark matter consists of matter whose nature we have yet to divine, and which gathers more diffusely than ordinary matter does. Otherwise, we would detect the gravity of concentrated chunks of dark matter dotting the universe: dark matter comets, dark matter planets, dark matter galaxies. As far as we can tell, that's not the way things are. What we know is that the matter we have come to love in the universe, the stuff of stars, planets, and life, is only a light frosting on the cosmic cake, modest buoys afloat in a vast cosmic ocean of something that looks like nothing. During the first 500,000 years after the Big Bang, a mere eye blink in the 14 billion year sweep of cosmic history, matter in the universe had already begun to coalesce into the blobs that would become clusters and superclusters of galaxies. But the cosmos would double in size during its next 500,000 years, and continue growing after that. At odds in the universe were two competing effects: gravity wants to make stuff coagulate, but the expansion wants to dilute it. If you do the math, you rapidly deduce that the gravity from ordinary matter could not win this battle by itself. It needed the help of dark matter, without which we would be actually not living in a universe with no structures, no clusters, no galaxies, no stars, no planets, no people. How much gravity from dark matter did it need? 6 times as much as that provided by ordinary matter itself. Just the amount we measure in the universe. This analysis doesn't tell us what dark matter is, only that dark matter's effects are real, and that, try as you might, you cannot credit ordinary matter for it. So dark matter is our frenemy. We have no clue what it is. It's kind of annoying. But we desperately need it in our calculations to arrive at an accurate description of the universe. Scientists are generally uncomfortable whenever we must base our calculations on concepts we don't understand, but we'll do it if we have to. And dark matter is not our first rodeo. In the 19th century, for example, scientists measured the energy output of our sun and showed its effect on our seasons and climate, long before anyone knew that thermonuclear fusion is responsible for that energy. At the time, the best ideas included the retrospectively laughable suggestion that the sun was a burning lump of coal. Also in the 19th century, we observed stars, obtained their spectra, and classified them long before the 20th century introduction of quantum physics, which gives us our understanding of how and why these spectra look the way they do. Unrelenting skeptics might compare the dark matter of today to the hypothetical, now defunct ether proposed in the 19th century as the weightless, transparent medium permeating the vacuum of space through which light moved. Until a famous 1887 experiment in Cleveland showed otherwise, performed by Albert Michelson and Edward Morley at Case Western Reserve University, scientists asserted that the ether must exist, even though not a shred of evidence supported this presumption. As a wave, light was thought to require a medium through which to propagate its energy, much as sound requires air or some other substance to transmit its waves. But light turns out to be quite happy traveling through the vacuum of space, devoid of any medium to carry it. Unlike sound waves, which consist of air vibrations, light waves were found to be self-propagating packets of energy requiring no assistance at all. Dark matter ignorance differs fundamentally from ether ignorance. The ether was a placeholder for our incomplete understanding, whereas the existence of dark matter derives not from mere presumption but from the observed effects of its gravity on visible matter. We're not inventing dark matter out of thin space, instead, we deduce its existence from observational facts. Dark matter is just as real as the many exoplanets discovered in orbit around stars other than the Sun, discovered solely through their gravitational influence on their host stars and not from direct measurement of their light. The worst that can happen is we discover that dark matter does not consist of matter at all, but of something else. Could we be seeing the effects of forces from another dimension? Are we feeling the ordinary gravity of ordinary matter crossing the membrane of a phantom universe adjacent to ours? If so, this could be just one of an infinite assortment of universes that comprise the multiverse. Sounds exotic and unbelievable. But is it any more crazy than the first suggestions that Earth orbits the Sun? That the Sun is one of 100 billion stars in the Milky Way? Or that the Milky Way is but one of 100 billion galaxies in the universe? Even if any of these fantastical accounts prove true, none of it would change the successful invocation of dark matter's gravity in the equations that we use to understand the formation and evolution of the universe. Other unrelenting skeptics might declare that seeing is believing, an approach to life that works well in many endeavors, including mechanical engineering, fishing, and perhaps dating. It's also good, apparently, for residents of Missouri. But it doesn't make for good science. Science is not just about seeing, it's about measuring, preferably with something that's not your own eyes, which are inextricably conjoined with the baggage of your brain. That baggage is more often than not a satchel of preconceived ideas, post-conceived notions, and outright bias. Having resisted attempts to detect it directly on Earth for 3/4 of a century, dark matter remains in play. Particle physicists are confident that dark matter consists of a ghostly class of undiscovered particles that interact with matter via gravity, but otherwise interact with matter or light only weakly or not at all. If you like gambling on physics, this option is a good bet. The world's largest particle accelerators are trying to manufacture dark matter particles amid the detritus of particle collisions. And specially designed laboratories buried deep underground are trying to detect dark matter particles passively, in case they wander in from space. An underground location naturally shields the facility from known cosmic particles that might trip the detectors as dark matter imposters. Although it all could be much ado about nothing, the idea of an elusive dark matter particle has good precedence. Neutrinos, for instance, were predicted and eventually discovered, even though they interact extremely weakly with ordinary matter. The copious flux of neutrinos from the Sun, 2 neutrinos for every helium nucleus fused from hydrogen in the Sun's thermonuclear core, exit the Sun unfazed by the Sun itself, travel through the vacuum of space at nearly the speed of light, then pass through Earth as though it does not exist. The tally, night and day, 100 billion neutrinos from the Sun pass through each square inch of your body, every second, without a trace of interaction with your body's atoms. In spite of this elusivity, neutrinos are nonetheless stoppable under special circumstances. And if you can stop a particle at all, you've detected it. Dark matter particles may reveal themselves through similarly rare interactions, or, more amazingly, they might manifest via forces other than the strong nuclear force, weak nuclear force, and electromagnetism. These three, plus gravity, complete the Fab Four forces of the universe, mediating all interactions between and among all known particles. So the choices are clear. Either dark matter particles must wait for us to discover and to control a new force or class of forces through which their particles interact, or else dark matter particles interact via normal forces, but with staggering weakness. So, dark matter's effects are real. We just don't know what it is. Dark matter seems not to interact through the strong nuclear force, so it cannot make nuclei. It hasn't been found to interact through the weak nuclear force, something even elusive neutrinos do. It doesn't seem to interact with the electromagnetic force, so it doesn't make molecules and concentrate into dense balls of dark matter. Nor does it absorb or emit or reflect or scatter light. As we've known from the beginning, dark matter does, indeed, exert gravity, to which ordinary matter responds. But that's it? After all these years, we haven't discovered it doing anything else. For now, we must remain content to carry dark matter along as a strange, invisible friend, invoking it where and when the universe requires it of us.